The magnitude or length of a vector is the distance from the origin to the terminal point of a position vector. In the case of not a position vector, we'd say the distance between the tail and the tip of the vector. And I'm kind of defining magnitude or length here, so I'm going to underline that, make it pop for you. And I've drawn for you a vector here, A, which has components A, B, and C. And since we're talking about the distance from the tip to the tail, or the distance from the head to the origin, it should make sense that we're going to use the distance formula. The magnitude of A is, notationally, it looks like an absolute value and is the square root of A squared plus B squared plus C squared. In the case of a two-dimensional vector, C would be 0, and this would look like the hypotenuse of a right triangle. Some books also use like a double absolute value to indicate that it's the magnitude of a vector. The scaled vector that I'll call dA has magnitude d times the magnitude of A. I'm using d only because I've already used up A, B, and C. And the idea here is we talked about the scalar multiplication changes the length of a vector, and this is enacted in when we compute the magnitude of a vector. And I leave it to you to do a little bit of arithmetic to see why that would be true. We consider special kinds of vectors. A unit vector has length 1. That is to say, if u is a unit vector, then the magnitude of u is equal to 1. Unit vectors can be good to work with because knowing that the length is 1, we effectively end up getting a direction out of that vector. Let's look at an exercise that puts some things together. Find a unit vector that has the same direction as a given vector, -5, 3, -1. I'm just for identification, just for label purposes here, I'm going to call that vector v. Now when we say this vector has the same direction as the vector v, that's actually another way to say that they're parallel. Unit vector or not unit vector, one vector is parallel to another vector if one is a scalar multiple of the other. And so the scaled vector c times a is actually parallel to the vector a. They point in the same direction. Actually, that would be the case also if c was negative. They point in opposite directions, but their angles are all the same. So I'm actually going to characterize that as one is a scalar multiple of the other. Well, that's just kind of a parenthetical thought. If we need a vector that points in the same direction as v, we're going to start with the vector -5, 3, -1, and we want it to have a magnitude of 1. Well, I don't know what the magnitude of v is, but it looks like it's not going to be 1. And so what we need to do is we need actually to find the correct number that we can multiply the vector v by so that the magnitude is 1. That number is going to be the actual magnitude of v. We'll see how this works. First, let's find the magnitude of v. It is -5 squared plus 3 squared plus -1 squared. And so here we can say that the magnitude of v is equal to the square root of 35 by doing some quick arithmetic there. So v is a vector that has a magnitude of almost 6. I'd like it to be a magnitude of 1 so that it's a unit vector. If I divide the vector by its magnitude, then I end up with a vector that looks like -5 over the square root of 35, 3 over the square root of 35, -1 over the square root of 35, and the number I was talking about, c, that we ended up multiplying by, was actually 1 over the magnitude of v. I leave it to you to do the arithmetic to see that the vector that we just created does indeed have a magnitude of 1. Continuing on with our idea of unit vectors, we're going to talk about 3 special unit vectors. In R3, there are 3 special unit vectors. One of them is called I. It is 1, 0, 0. One is called J. It is 0, 1, 0. And the third is K. It is 0, 0, 1. Notice that I, J, and K have hats, but they're special hats. They look like little the caret from your keyboard, and we use that to denote that these are actually unit vectors. And I'm going to identify them in the x, y, z coordinate system, and I'm going to use some colors here. In blue, we're going to look at the vector I. I'm going to thicken this up too. And it has a x component of 1, and then y and z components are 0. And so it's going to be along the x-axis. It's going to hit the point 1 on the x-axis, and that's the vector we're going to call I. Similarly, j has 1 as the y component, 0 for the x and z components, and so it will come out along the y-axis and have a length of 1, and that's our vector j. Our vector k, having 1 as the z component, is going to be the vector that comes up the z-axis and is 1 unit long. Now these three vectors are, they meet each other at a 90-degree angle, and it is actually the case that I, j, and k span V3. That is to say that any vector in V3 can be written as a linear combination of these three vectors. Let me show you what I mean. In the previous example that we looked at, we were looking at the vector -5, 3, -1. I can rewrite V by taking apart its components, -5, 0, 0, plus 0, 3, 0, plus 0, 0, -1. And then by expressing this using scalar multiplication, we can say we've got -5 times the vector 1, 0, 0, plus 3 times the vector 0, 1, 0, plus, well, let me change that, -1 times the vector 0, 0, 1. And those are the representations that we had for I, j, and k. And so we can write this as -5i plus 3j minus k, of course dropping the 1 as a coefficient. So we can actually conclude that the vector given in angle brackets, -5, 3, 1, is the same as the vector given by -5i plus 3j minus k. And these, it's just actually two different notations that we can use. You will see in the textbook and in my work, you'll see angle brackets. You will also see I, j, and k. It's up to you just to reconcile that those two mean exactly the same thing. Now, because of this linear combination possibility here, we say that I, j, and k actually form a basis in V3, and these, that just means that they span V3. But that they're unit vectors, that they are in the x, y, and z directions respectively. What we say is they are called the standard basis vectors for V3.